Have you ever really thought about what happens when you hit send on an email? Or when you load a web page? There is this incredible high-speed logic puzzle that's constantly running behind the scenes. And today, we're going to dive right into that puzzle by explaining routing, the invisible, fundamental process that makes the entire internet actually work.
I mean, think about it for a second. Your little data packet gets launched into this massive global network with millions, maybe billions of possible paths. How on earth does it find its way from your computer to a server on another continent in the blink of an eye and do it perfectly every single time? Well, it's not magic, that's for sure. It's a really brilliant system of logic.
The secret is, these packets are just following directions, and those directions are given to them by special devices called routers. The best way to think of a router is like the internet's traffic cop. They stand at every single digital intersection, just directing this constant flood of data and pointing each and every packet in exactly the right direction.
So, at its core, a router really only has two main jobs. First, it has to figure out the absolute best path for data to travel. And second, once that decision is made, it's got to actually forward the data along that path. These two functions, right? Path determination and packet forwarding, that is the heart and soul of routing.
So let's start with that first job, path determination. How does a router actually choose the best path out of all the options? To figure that out, we need to look inside its brain, which is something called the routing table.
The routing table is, pretty much exactly what it sounds like. It's a map. When a data packet shows up, the router looks at its destination IP address, which is basically the mailing address on an envelope, and it checks it against this map to find a route that matches. But what happens if more than one route on that map matches the destination?
Well, in that case, it follows one simple, unbreakable rule, the longest match rule. What this means is if a bunch of different routes all match a destination, the router will always choose the most specific one. And that specificity is measured by its prefix length. Just think of it this way. A longer prefix is a more precise address. When it comes to routing, more specific is always better.
Okay, let's see this in action, because it makes it way clearer. Imagine a packet is trying to get to the IP address 172.16.0.10. The router checks its table, and as you can see here, it finds three potential matches. That destination fits inside the /12 network, and it fits inside the /18 network, and it fits inside the /26 network. So yeah, all three are technically valid matches.
So which one wins? Well, it's always the one with the longest prefix length. In this case, 26 is longer than 18 and 12, which makes that /26 route the undeniable winner. It's kind of like this. The /12 route is like telling the packet to go to California. The /18 is like saying go to Los Angeles. But the /26 is the specific street address. A router's always going to pick the most precise address it has. The longest match always wins, period.
Okay, so now we know how the router uses its map to make a decision. But that brings up a pretty obvious question, right? Where does that map, the routing table, even come from? I mean, they don't come with it programmed at the factory. Routers actually have to learn this stuff.
So, a router builds its map in three main ways. First, it automatically knows about any networks that are physically plugged right into it. That's a given. Second, a network admin can go in and manually program specific directions, and we call those static routes. Or, and this is where things get really cool, routers can actually talk to each other and learn the map automatically using what are called dynamic routing protocols.
But of course, this creates a new little puzzle. What if an admin manually programs a static route to a network, but then the router also learns a dynamic route to that very same network from one of its neighbors? Now it's got conflicting information from two different sources. Which one is it supposed to trust? To solve this, the router uses a concept called administrative distance, or AD for short. You can just think of it as a trustworthiness score for every source of information, ranked from 0 to 255. And the rule here is incredibly simple. The router will always believe the source with the lowest AD score. The lower the number, the more trustworthy the source. This table here shows that trust hierarchy perfectly. A directly connected network has an AD of 0. I mean, you just can't get more trustworthy than something you're physically plugged into. A static route, which an admin typed in by hand, is right behind it at 1. And then below that, you've got the various dynamic routing protocols. You can think of these as different languages routers use to share their maps, like EIGRP, OSPF, and RIP.
And as you can see, they each have their own trust score. So back to our question. If a router learns a route from a static entry with an AD of 1 and also from the OSPF protocol with an AD of 110, the static route wins every single time because its trust score is lower.
At the end of the day, static and dynamic routing aren't really competitors. They're just different tools for different jobs. Static routes are like giving someone a single printed out map. It's simple, it's secure, but if there's a road closure, well, it's totally useless. Dynamic routing, on the other hand, is like having a live GPS that's constantly updating for traffic and outages. It's more complex and resource-intensive, sure, but it adapts to a changing world on the fly.
All right, so the router has built its map, it's used its rules to pick the single best path. Now comes its second big job, forwarding the packet. Let's follow a packet on just one single hop of its long journey to see exactly how this works. This whole process is basically a 5-step dance. A frame arrives at the router unwraps it to get to the IP packet inside, it does its lookup, just like we talked about, to find the best path, and then, and this is a really key part, it wraps that original IP packet in a brand new frame, one that's tailored specifically for the next leg of the journey before it sends it on its way. That outer wrapper, that frame, it gets rebuilt at every single router the packet crosses. Now, to handle the insane amount of traffic we have today, this process had to get incredibly fast. The very first routers used something called process switching, where the main CPU had to make a decision for every single packet. As you can imagine, that was a huge bottleneck. Then came fast switching, which was smarter, it cached decisions. But today, the standard is CEF, or Cisco Express Forwarding. It basically pre-calculates all the forwarding information ahead of time, so when a packet arrives, the decision is already made. It bypasses the main CPU entirely, which gives it that blazing fast performance we need.
Okay, so let's zoom all the way back out again. We've seen how a single router makes a single decision. But how does this possibly scale up to the entire internet? It works because of a few simple, but actually pretty profound principles that create what you could call a coordinated global dance.
First, every single router on the internet acts independently, using only its own local map to make a choice. Second, this means that one router's map might be completely different from its next-door neighbor's. And third, just because a packet can find a path to a destination, that doesn't automatically guarantee it knows a path to get back. The return path has to be figured out separately. It sounds almost chaotic, but this system of independent agents creates a remarkably resilient network. And this leads to a really mind-bending conclusion. The internet isn't one giant, perfectly synchronized machine. It's actually, as the source material puts it, a complex distributed system making countless independent decisions that somehow collectively keeps everything connected. Billions of tiny individual choices, all following these simple rules, create the global network we all rely on every day.
So the next time you click a link, maybe just take a half-second to appreciate the wild journey your data is about to take. It's a journey guided by this invisible, high-speed logic, a truly intricate dance of rules and algorithms that, against all odds, just works.